So let's start with zero order. Zero order means I have an A going to some products. And the rate equation will be R equals K of A to the 0, which is odd, which means the rate of reaction is independent upon the concentration of A. Kind of strange. The concentration of A does not drive the speed of the reaction. Now, they are far and few between, but we have some important reaction. The light reactions in photosynthesis are 0th order. Okay, so you need to have that kind of light to spur on the reaction forward, not the concentration. But you still have to have A there. Without A, of course, the reaction doesn't work. And if you look at the graph of the rate of a 0th order reaction, what you're going to get is you're going to, over time, the rate's going to stay constant because it doesn't depend on the concentration. And this slope we're going to find is equal to K. All right, so let's look at this carefully. All right, so what I have here is I have R, again, is equal to A naught. Let's just rewrite this. So R is equal to the rate law constant, A to the 0. And since it's A to the 0 is 1, this whole thing goes to 1. So if R equals K. All right, so I know that the rate equals K. Now the rate can also equal something else. It can also equal the negative change of my A over time. Certainly A is going to get used up. And that's, of course, going to be all over the change in time. Okay, now let's rearrange this and let's actually make a differential out of this. Let's make this a derivative because a change in time is from 2 points. Let's make those 2 points very small. So the disappearance of A is also can be considered the rate. Rate, we look at the what? The amount of A, and also the disappearance of A can also give us the rate. All right. Even though the change in the concentration doesn't drive the reaction, we are going to get this disappearance of A over time. All right. In any case, that being said, let's continue on. Now, I want to change these changes into small little points. I don't want to use big gaps between a line and make a what? An average between them. I want to make these 2 points infinitely small, so we make a differential or a derivative. So we're going to change this to negative d of A all over dt. Same thing. So we're going to take the differential of the A and the differential of the time. And that's what we're doing here. See, what we just made here is something called a differential equation. All right? So we've made the rate on one side equal to the rate at a instantaneous point. And it's very important to understand that rates are generally instantaneous points. When you think about it, when you do a rate of reaction, most of the time, now 0 order is kind of weird, but most of the time when they're first or second order, we have a concentration of A that gives me some rate, but that's the initial. See, it only gives me the initial rate once I know the initial concentration. Well, over time, that changes. That's the thing, the concentration of A is changing over time. It's a nonlinear function, and so the rate changes over time. So what we're trying to do here is we're trying to make, link up what this equals to a derivative, or to, in this case, I say differential, but it's called a derivative, 2 small points. So I made this derivative, and I made this point here, and it's called a differential equation. And it's great. It's a nice differential equation. We have the instantaneous point of that reaction as it starts, point before it, goes down, or whatever it might do. Okay, I know I kind of gave it away here, but we're looking for that point, instantaneous point, 2 points that are approaching each other, limit to 0. I'm looking for those 2 tiny little points. All right, well, how helpful is it to be talking about that point there? I want to know about other points. I want to know in time t, okay, what's the concentration or what's the rate going to be? So that's not helpful. So what I want to do here is I want to integrate. Right, I want to take this differential equation and I want to integrate. But before I do that, I'm just going to do some manipulation here. I want to bring this dt over here. So I'm going to bring the negative over to this side. So I got d of A equal negative k d of t. All right, and now I'm going to do I'm going to do an integral. Integral is like a little sum, a little fancy s, the sum of all the integrals. So now I'm dealing with finding that volume of water coming out of the spigot that I just talked about. Or I'm trying to find under a curve, trying to find that one slice of differential. What is the value of that, of A, let's say, under a certain time period? So in any case, very important stuff here. I'm going to take the differential from A. Now this is called a definite integral, so I'm definitely adding up these or multiplying or adding up these little infinite slices, these differentials, okay, to some region, some couple of points. Well, the point is from A0 initial to A of some time period. It's not going to be original A. A is going to change. There's no question about it. Even though it doesn't change the rate, it definitely goes down over time. And then, of course, we're going to go from T0 to some time. And that's what we're going to do. And when we do that math, okay, what do we get? Well, we're going to get, okay, we get the integral of dA. What we're going to get is we're going to get A of t, concentration, minus A of 0. That's our solution. Difference between these points. We're going to get the A of t to the A of 0, which is initial. That's what all of this gives me when I integrate, which essentially is the original derivative, right? And I'm going to take the integral of this derivative. I get back out the derivative, right? So I'm going to integrate this. I get back out A of t. So if I do, it's the opposite. But in any case, I do the same thing over here, and it equals what? Well, t of 0 is 0. So I don't do t of 0 minus. So basically, I'm just going to do negative k. And I'm going to do, and by the way, this was a constant. So this constant doesn't really should be outside the integral. But negative k doesn't change. And I just get t, just temperature. I'm sorry, time, I should say. All right, and it's a time at some point beyond 0. T0 is not here because it's just 0. And this is my equation, my integrated equation, that links concentration changes with time. Because what I'm doing is I'm finding the time by which I can find that slice from that whatever curve or function I have. Okay, so that's time, and this is definitely going to be A of concentration of A now. So this becomes how much of A, just like we talked about before, how much water. By integrating this rate of change, this derivative, I now get the total amount of A at a certain point. I find exactly this slice of time, I find exactly what A equals at this slice of time, how much A was added if I know how the slope is changing over time. So that's what this does for us. So now I can solve for temperature if you give me what? If I know the initial concentration, the final concentration, knowing the rate law constant, I know how much time it takes for it to go down. Very important stuff. Now, as we go forward in this, though, there's even some more implications to this. Now, what are they? Well, if I rearrange this one more time, as the song goes, and I get rid of this, and I go A of t equals negative kt to plus A0. I don't know what I'm doing here, A of 0. Now, what am I doing here? Let me just write this over here. So A of t, right? I brought this over to this side algebraically, so I just plus both sides. Gives me negative kt. Make great band names, right? Negative kt. They would be thinking for years what that means. That'd be kind of cool. I love it. In any case, plus A of naught, which is the original A concentration. Now, why did I do this? Well, my friends in chemistry, Y equals mx plus b. We have found a way to take something that's nonlinear and make it linear. And what we have, my friends in chemistry, is a graph. And if I was to graph the A concentration to the time, which is my x, right here, I get a negative k, negative slope, and the y-intercept, okay, is right here. So I get a negative. So anytime someone says to you, hey, if it's 0th order, what does that mean? Well, it means that if you graph it this way, you will get a linear line if your y-axis is the concentration of A over time. And if that line has a negative slope and is linear, you know you've got an order that's 0. So you don't have to, so it's another way to evaluate whether a reaction is 0 or not. And that would be to take the reaction and see if it makes a straight line with its values by taking the concentration changes over time. Notice the concentration changes go directly down. There's no curve in it. And the reason why there's no curve in it is because it's not dependent upon the A changing. Okay, so the rate, okay, over time, that's K, because rate equals what? K, right, because this is going to 1. And if I take the integral of the rate, this is how much the water flows, what kind of graph do I get now? I get this down here. All right, so let's go now to first order. That was 0th order, and this is first. Now, in truth, this is the first order I'm going to do. I have A going to products, and it depends on that A. So my rate law is equal to the rate constant times A to the first. And that's a first order. All right? And my rate is equal to A. Now, if I was to graph this using rate, using the change over time, which is a derivative, okay, I would get something like this. Very famous curve. All right, we'll get back to that. Let's get back to this. R is equal to K to the A1. Well, what else is it equal? As we talked about before, it's also equal to the negative, or the disappearance, the change of the concentration of A over the change of time equals K times A. All right, let's make these changes infinitely small compared to each other. Let's make them differentials. So negative dA over dt equals K to the A here. That's pretty simple. Now we're going to bring the dt up and the negative up, so I get, this case I'm going to bring this down. So I'm going to simplify this by bringing the negative over, negative K, the dt over, negative K dt. I'm bringing this A down. So what I get is d of A, which is already there, 1 over A. Okay, and that is my differential equation, and now I'm putting the concentrations on one side because I want to evaluate them compared to D. All right, now what we're going to do is we're going to integrate, because again, it's not good to know a point. I want to know a point on my graph that tells me how much, not just what the rate is. Because at this point, all I can have is an instantaneous what? Position at a certain time. I know the what? I know the slope, the rate of change. And of course, that slope is constantly changing. How the heck do we figure out how much A we have if stuff keeps changing? Well, we do this integration. So we're going to integrate this. Notice I'm keeping my constant out. And I'm going to integrate all of this. And I'm integrating from A at some time period. Remember, this is a definite integral to A initial. And this, of course, is going to be time, time t, and this is time 0. Same thing. All right, now when I integrate, okay, I'm now able to take how much water came from the spigot, or how much A do I have, not just what the change of A is. From the change of A, I get how much A. That's what we do to integrate here. In any case, 1 over a, okay, the integral of that, okay, is ln natural log of a. Of what? T minus the natural log of a0. That's what we get. This little d just tells me I'm dealing with what? A differential, tiny slices of a, tiny slices of t. Don't get lost there. All right, so what I just did was, there's a proof for this, but there's, if you remember your rules, the natural log of a, okay, if you do the derivative, is 1 over a. So because integrals and derivatives are opposites of each other, that's why this works. Okay, now, of course, that equals negative k, and I get t again. The reason why I don't have t0 is 0, so that's why I don't have this arrangement. Okay, so there's my integrated first order formula. All right, now, as I did before, let's rearrange this. I got ln of a, the concentration of a to some time period, equals negative kt plus the ln of a, natural log of a initial. So this is my y, mx plus b. So we took a curve that wasn't straight and we straightened it out. So let's go find that curve, what it looks like. So my y is, in this case, the natural log of a. By the way, that a0 would be my what? Y-intercept at that point. And then the change in that is ln of a. Time period here. Notice my slope is negative. And I get a negative line. So I get a negative slope. So if I have no information, but somehow we took different, during the reaction, different concentrations of A along the time period of the reaction, we did a natural log of it, and we plotted the natural log of those concentrations over time, what we would get is a straight line. And this negative curve with ln of A on the y-axis shows us that this is first order. So we can actually look at the graph of the information and see if it matches. If you get a straight line with a negative curve and it's the ln of A that is used to do that, you have definitely a first order. It's another way to evaluate the orders of a reaction. Now above, if we get a negative what? Slope, like we did the first zero order, I'm sorry. If we get a negative slope, but the y-axis is just a concentration of A over time, my friend in chemistry, we have a zero order. Okay, now a zero order, remember it started out looking like this, r equals k, and then the integral is this negative curve going downward, but using what? The concentration of A. Well, in first order, we have this curve, which is a very classic half-life curve, and the integral of that rate, flow of water, gives me how much A? How much A at a certain time period? Pretty cool. Okay, now first order is by far the most frequent in our chemistry, and one of the ones to think about is radioactive decay. This is like a half-life curve, right? So this could be 5 days right here, and this could be, I don't know, 1 gram, and then right here we have what? 10 days. That's on the scale, and then we have 0.5 grams. So that's a classic half-life curve. So radioactive decay is a definite first order. All right, any case, that is first order. Let's do second order. A little faster now. So second order, I would have this scenario. I would have A plus A giving me products. And the rate law, R, is equal to K A squared, concentration of A squared. And of course, if you graph the rate over time, it's going to do something like this also. It'll look a little different than the other one. In fact, it won't bottom out as much. Let's do that again. Whereas the half-life would go to the bottom, this would wouldn't bottom out because of that square. So this would be second order. And first order would actually look more like that. Okay, but that's what we get. In any case, moving forward, let's differentiate our equation. Okay, that must be equal to the what? Equal to the disappearance of A, right? So the negative change of A over the change of time equals K squared. And we do the differential, we'll do the differential and make this smaller, so we get negative d of A over d of t equals K A squared. Okay, bring the A's down and bring the dt up. What do we get? We get negative KT d of A, and also 1 over A squared. All right, now we're going to integrate like we've done before. That's the sum. And I'm sorry, that should be a dt, because I brought the dt up. Jumping my gun here. Okay, when we integrate, of course, integrate, we're going from A, from some time period, from the initial, and here's the initial, A of 0. This is time of 0, and time. And what we get, okay, is, well, 1 over A squared, and that's another function. There's a rule that the integral of 1 over something, like 1 over x A squared, or 1 over x, so 1 over x squared is equal to the, if you integrate that, that becomes negative 1 over x, of course, plus a constant. Don't worry about the constant. That's just like the starting position of what you started with, like how much water. But so we won't consider ourselves the constant. So that's a function, and that's, of course, one of the rules you see, because the I believe the derivative of negative 1 over x is 1 over x squared. So what we do here, knowing that rule of integrals, and again, there's a proof for every rule. I don't remember all of them, obviously. But what I get is, I get negative 1 over A, okay, minus 1 over, that's A of t, sorry, going from t to A, minus 1 over the concentration of A to 0, which equals negative K, for the same reason it's T. Multiply this side by negative. Get rid of negative, that becomes a positive KT. And this becomes 1 over A of T minus 1 over A of 0. And that is your second order integrated equation. If you want to rewrite it from my Y, 1 over concentration of A to the T equals KT, oops, sorry, a little doohickey there, KT plus 1 over A to the 0. And when we do that, we get our Y equals mx plus b. So when we graph this, the graph on the y is going to be 1 over the inverse of a. This will be t. Look at the slope. It's positive because of that rule from that integral rule. So kt becomes a positive value. So it's a positive line. So if you get a positive slope and your y-axis is 1 over a, we know that immediately this must be second order. So second order. So we can use graphical analysis to figure out our orders. We don't have to look at the experiment in terms of changing initial concentrations. So this is our derivative. And you take the derivative and you integrate it, the rates, you get how much? And look at that. So now we have these equations where we can actually, again, given a time value, knowing the what? Rate constant, if I give you the initial concentration over some time period, you can give me exactly what that slice is at that time period. And that's what that's all about, exactly what that slice is. All right, so exactly at time t, what is that slice? What is that amount at that small little infinite slice of time? And that's the power. If you look at your reference tables, you'll see these listed, okay? And that's how we use them. Anytime you're dealing with changes in concentrations and how much time you need, and linking time with now concentrations, how much, we use the integrated rate law formulas. And there they are in all their glory. No, that's not that. It's not what I wanted. So let's go over where they are. So here is this formula here. That's for second order. This, of course, is for first order. And, of course, this is for 0th order. Hope that helped.